You know, in the last video we talked about an apple. An apple had potential energy. We also talked about a guy with a slingshot. Slingshot guy had potential energy, at least the rock did, because the energy was of position. Once that rock is released, once that apple falls, we actually have motion. Since we actually have motion, we have kinetic energy. Kinetic energy is exactly that, energy of motion. So when you're actually doing something, you're using kinetic energy. Here we have this guy going down the hill on a skateboard. He is actually moving. Energy is defined by the fact that you are moving. So you have kinetic energy here. Now we do have a formula for kinetic energy, and we're actually going to calculate some of that later on, but you can see it's right here. 1/2 mass times, well, V is going to be the speed. So this is going to be speed squared. So yes, the speed of an object counts more than the mass of an object. And that's the reason why you have such dangerous car crashes. The faster the speed, that's why a small football player can run over a big football player if he's gathered up enough speed. That's just kind of the nature of kinetic energy, you might say. Now, kinetic energy still measures work. So the mass is going to take into account, because that is a factor. It's just that speed is going to count more, you might say. And yes, all of this is going to be measured in joules, just like gravitational potential energy was in the last one. Now, I want to be clear about this kinetic energy. At the top of this hill, the ball has zero kinetic energy. It's not moving at all. Kinetic energy is defined by movement, but it has all kinds of potential energy. Potential energy is that it will fall, and you can see here it says greater than zero. Has potential energy here, no kinetic energy here. But in the process of falling, it has both. It has potential energy because it can continue to have the potential to fall more, and it has kinetic energy because it is actually doing something. At the bottom of the hill, it has stopped. It has stopped, so it has no more potential energy. Has no more potential energy, and if it is stopped, it's not going to have any kinetic energy. I know it says that it has some here, but that would be if it is still moving. So it would be if all the energy is spent up, then we have no potential energy and no kinetic energy either there. Let's take a look at this next slide. Okay, here's where we're going to calculate the kinetic energy. Now this is not the last slide of our video. This is just kind of in the middle here. Okay, say we have a cat that is 12 kilograms. Now that would be one ginormous cat. That's like the King Kong of all cats. I don't know why I put 12 kilograms, but we'll have to run with it. Cat has 12 kilograms and he is traveling at 8 meters per second. So Ke equals 1/2 times 12 times 8 squared. And I figure we probably ought to go ahead and get that 8 squared out. So that 8 squared is 8 times 8, which is 64. So we have 1/2 times 12 times 64. Let's go to our dashboard. 1/2 is 0.5 times 12 times 64 equals 384 joules. So the kinetic energy equals to 384 joules. What if we have this car? You know, we'll probably have a little bit more energy coming here. This car that is 1,200 kilograms and is traveling at a higher speed, 34 meters per second. I may have to do some bigger calculations here. Kinetic energy equals 1/2 times 1200. Now, I know there's a way where you could just go ahead and divide that out and make that 600, but I don't think I will in this case. It'll come up with the same answer anyway. But it's times 34 squared. So we probably should go ahead and get that 34 squared taken care of, which is 34 times 34. Ooh, this is going to be a huge one. We have to use scientific notation on these. 1,156. So we're going to mark that out and make it 1,156. So, wow. Let's go with 0.5 times 1,200 kilograms times 1,156. I believe that's what it was. Equals, let me make sure that's 1,156. Yes, it is. So what did we have? 693,600 joules. Ooh, 693,600. 693,600. And if we were to put that into scientific notation, it would be 6.94 times 10 to the 5th power. Let's talk a little bit about mechanical and non-mechanical energy. The sum of potential and kinetic energy is called mechanical energy. The sum of potential energy plus the kinetic energy. So if you have that ball on top of the hill, you have all the possible energy of it falling, adding up with all the energy of it falling. So back there you would have the same equivalency at the top because you're taking potential energy. You have a lot of it, but not a lot of kinetic energy. In fact, no kinetic energy. And that should equal, if you were to add the potential energy and kinetic energy here, and same thing down there, even though you would all have kinetic energy if it has not stopped. So potential energy plus kinetic energy equals the mechanical energy. Now, we're actually going to talk a little bit more about non-mechanical energy. You may remember that even a solid has molecules that vibrate, and that's why I used this example right here. Even a solid has molecules that are vibrating, and the more heat you add to it, eventually those molecules will go faster and will turn to liquid. Eventually those molecules will go faster the more heat you add and turn to gas, turn to vapor. So in all this movement inside every molecule, I mean the computer you have, the pencil you're writing on, the hair on your head, it's all having some kind of energy because of the movement in it. And that's called non-mechanical energy. The energy that lies at the atomic level, the molecule level, and does not affect motion is called non-mechanical energy. That ball at the top of the hill, sure, it's moving inside, but it's not affecting the actual motion, but it does have some non-mechanical energy. So the kinetic energy of these particles with temperature goes solid, liquid, gas, increases the non-mechanical energy. Now, in a chemical change, I guess I should have had this arrow here. In a chemical change, you have something called chemical energy. Now, let me show you what a chemical change was. Here we had two atoms, the oxygen and the CH4, which added together to become carbon dioxide, that's what this is, and two waters. Instead of a physical change like the sheep where the wool is still wool, here we have a chemical reaction, a chemical change where you actually are changing chemicals like a nail rusting, like food digestion, like a match burning. You may remember some of these. That is called chemical energy, and for every time you have some kind of change of chemicals, you have to have the energy in which to do it, and that's called chemical energy. Some of these have more kinetic energy. The chemical energy is kinetic energy. Some of it has more actual kinetic energy than others. A match burning has more kinetic energy than, say, a nail rusting. A nail rusting doesn't really show much action. It's very slow action. But the match burning contains a lot more. And the energy for us, we humans that have funny figures here, the energy for us is actually chemical energy. It's actually chemical energy here. Because here's what happens. Our muscles, our ability to make energy, to move around, comes from the breakdown of food, comes from the digestion. The food and the digestion gives us energy. And the respiration does also. It's part of that process. The energy of our food, of course, comes from eating either plants or animals, and the animals that we eat can be directly eventually relayed back to some kind of plant. The plant photosynthesis gets energy from the sun. So yes, the energy we have in us indirectly does come from the sun. Now, how does the sun get its energy? The sun gets its energy by nuclear fusion, F-U-S-I-O-N. I'm not going to write it down right now. But fusion is forming large nucleuses, this kind of building things together, and I'm sure we'll talk about this much more in our book. But fusion and fission, F-I-S-S-I-O-N, fission is the splitting up of nucleuses. That's what power plants do. The splitting up of nucleuses and the forming together of nucleuses convert huge amounts of energy. So just atoms itself have a form of potential energy. Any atom up here can be split. Let's just say we have this carbon dioxide atom right here. If you were to split up the atom, or to split up a nucleus of one of these atoms, then it has the potential to have lots and lots of energy. So just having non-mechanical energy, the energy, subatomic energy, it is a form of potential energy. One more thing I want to talk about, there is such a thing as light energy. You know, there's energy from that nuclear fusion there, and we see it on a summer day on asphalt. That's an example. You know, the asphalt is going to heat up by electromagnetic waves. Whenever you get radiation heat from the sun, I don't know if I should use that term radiation or not, because that's kind of misleading. It's not the cancer treatment necessarily. But the heat from the sun on the asphalt is from electromagnetic waves. Now what happens is that's light energy. You feel the heat on that asphalt, and you can actually break down the spectrum and find where more energy is. The different light waves will end up going up and down, and you'll see that later on if you don't know it already. And you get more energy and more motion from the blue side of the spectrum of the rainbow than you do from the red side. And that's something that's I thought was kind of curious. Well, I hope you've learned a little bit about kinetic energy.